Hey guys, well, if you're looking at this, it's after the Mobius is due, but I just want to go over the questions just so everybody knows what they're doing and how they did that. Cool, let's start. So consider the piecewise function f of x equals 2x cubed minus 2x and x squared minus x4. And we have these over here conditions are two ways to read them. For which value of a does limit of xa fx exist? So for a limit to exist, if we remember, the limit x approaching a from the positive side should equal to the limit at x approaching a from the negative side. And basically what that means is for these two, you need to make them equal, because in that case, the two limits from both sides will be equal. So let's set it as equal. So 2x cubed minus 2x is equal to x squared minus x to the power of 4. If we factor them, we're going to get 2x x squared minus 1. And here we get x squared 1 minus x squared. So now we're going to just factor everything. So 2x is equal to x minus 1, x plus 1 is equal to x squared, 1 minus x, 1 plus x. And basically we see that they're equal under four conditions. If x is equal to 0, if x is equal to plus or minus 1, and these are easy to spot because that's when all of these would equal to 0. And then there's another one hiding there when x is equal to -2. Both of these would be equal. So if I were to select answers, it would be 0 and -1. Next. Okay, let's clear all drawings. Okay. If we know that limit f x approaching a f at x is equal to L, then it is possible that limit at x approaching a from the left side does not exist. This is not true because, again, as I just pointed out, we need, so limit x approaching a plus has to equal to limit x from the left side. And if one of them doesn't exist, that means that the other one can't equal to it. That's why that's wrong. Now this one, f of x equals L for all x, that's possible. And that is possible if you just have a line. So if you imagine our graph, if you imagine just a straight line, right, then for all f of x, you're going to be equal to the limit. So that's why this is true. Then fa is equal to L. This can be true, and that just means that what we approached is there. So again, if we just look at the line, for instance, if we picked an arbitrary point over here, then f at a at this point would equal to the limit. So this is definitely possible. Now the third one is a bit more tricky to see. And here, fa is equal to L plus 1. That's possible because, again, at the limit, we don't care what happens at the limit. We just care what happens while we're approaching the limit. And so what we can happen is we can have something that looks like this. Then there's a hole over here. We jump up 1, and then we continue. And in this case, the limit would exist, but f at a would equal to L plus 1. And so that's why this is also true. Let's go next. Great. Now this one, it's quite enjoyable once you understand what you're doing. So the way I like to think about this is, so let's draw our here, right over here. And let's draw our line. This isn't the exact line we have. And here I'll make it a straight line. There it is. And now let's remember the formal definition of everything, the formal definition of a limit. So right over here, and we're going to draw a kind of box. Bam, bam. Let's make it green again. I'm going to pretend I love Christmas. So, and then we're going to have our limit. So this over here, we're going to say that this is our limit. It happens at A. And now you'll see my beautiful handwriting again. I know everybody's excited. I've been having beautiful handwriting with mouse. So this is A, and this is the limit. And so right over here, that's the epsilon. We're going to have epsilon from both sides. And this is delta, so A plus delta, A minus delta. Okay, great. You can be thinking, well, why are you showing us this? This doesn't really matter. So what's happening here is now, if we remember, so limit, and this is the definition, so limit as x approaches a for f of x, this is equal to some limit, and then you know that that's true if f at x minus L, an absolute value of that, is smaller than epsilon. And at the same time, if while this is happening, this can have a range of x minus a, absolute value of that, is smaller than delta, but bigger than 0. Okay? And so now that this happens, let's put all the information we have together. So first, let's try to fill this in, because to find our a, we need to fill this in. So we know that our limit is -9, right? Because that's what we're approaching. So now what we need to kind of think of is, when are we approaching this? We can do this by seeing that if you plug in 2, x equals 2, you're going to get -9. So if we rewrite this over here, what that means is that limit, and our f of x is 4x minus 17, so limit of f of x when x approaches 2, that is equal to -9. Cool. Now what's going to happen is we need to fill in everything else. So now, if I'm just going to bring it over here, so this, I'm just rewriting over here, so absolute value of 4x minus 17 minus our limit, so minus -9 is going to be +9. It's going to be smaller than our epsilon, and our epsilon is 1/4, because we want it to be 1/4 unit away, so it's 1/4. Perfect. So now if we solve this, we're going to get absolute value of 4x minus 8 is less than 1/4. Then 4x minus 2 is less than 1/4. And the reason I want to get it to x minus 2 is because of our delta over here. So we know that also the range of this will be 0 is smaller than x minus 2, because what we're approaching is 2, is our a, is smaller than delta. And so now I'm kind of looking for my delta, and that's why I want to get x minus 2 over here, to know what that range is. So then x minus 2 is small, absolute value of x minus 2 is smaller than 1/8. So then if epsilon is equal to 1/8, and again, all of these are double implications, and why this is why this works. But if you don't have double implications, it should be fine. So it's 1/8. And so then we know that our delta can be equal to 1/8, and that's going to be the distance. So d is 1/8. So 0 is less than x minus 2 is less than 1/8, and this is supposed to be absolute value. And so now if we think about what is this asking? Well, it's basically asking if we had some limits over here, if we had a d which is smaller, right, that would be fine, because we would still get inside this epsilon. But if on the other hand we added a bigger d than was necessary and ended up over here, then we would be outside of our epsilon range. So to really boil it down, what we're basically looking is for a number smaller than 1/8. So now if we think about that, 1/16 is going to be smaller than 1/8, 17 is going to be smaller than 1/8, 3/160 is going to be smaller than 1/8, and 3/40 is smaller than. So it's all over here. Okay, great. So let's clear all drawings. So which of the functions below have at least one vertical asymptote? So when we're looking for a vertical asymptote, what we're thinking of is, so here we go. We're thinking of vertical asymptotes is when we have something over here and something is reaching towards infinity or negative infinity, right? And so that happens, for instance, if we have 5/x, if x is equal to 0, then we're going to have an asymptote, because as you approach 0, your value goes to infinity. Okay, so in essence, when you're looking for vertical asymptotes, you're looking at your denominators and checking if they're equal to 0. Okay, but you also have to be careful, and we'll see this in some of the examples. So wait a second, let's leave this up here. Okay, so let's look at the first one. So the first one, it does have x minus 4. So it does have a case where the denominator is equal to 0. That's at x equals to 1. Now what we need to check is whether this x minus 1 gets simplified or canceled out. Because if it does, what will happen is instead of an asymptote, we'll just get a hole. So let's see, let's factor the top. So we're going to get x minus 6. No, it's x plus 6 times x minus 1 over x minus 1. So over here, they do cancel out. So over here, even though at the bottom we would get, there is a condition for x equaling to 0, it would be canceled out, and so therefore there wouldn't be any asymptote here. Same thing actually happens over here. So x equals to 5, negative 5 would yield us an asymptote. But because x squared minus 5, we can factor it out into x minus 5, x plus 5 over x plus 5. The x plus 5s would cancel out, and therefore no asymptote would happen. Over here, even though again we have an x, it would be canceled out, and therefore no asymptote. And over here, x squared plus 3 never equals to 0, or never goes below. And you can think of that because if we have our regular parabola, and the regular parabola should not go under, it's like somewhere like this. If we move it up 3 units, it's never going to cross 0. And that's why we know that the fourth one also has no, it has no vertical asymptotes. Perfect. So now this one, I think this one was kind of tricky for a lot of people. So let's take a look at it. I'm saying like let's take a look, like I could just skip it while doing this, which is kind of funny, I think. But well. So what is it asking us? So basically we see how over here it's lopsided. So usually when we're taking our limit, if you remember before, we would have a plus d. Or sorry, I meant to say x minus a that is greater than 0 and less than delta. And that just represented that within our range, on the two sides, they're both equal. So, like if we have a regular function like this, right, and our epsilon is somewhere over here, then when we drop down and we have a over here, then the distances from a to both sides, where it's still going to stay inside the range of epsilon, will be the same, a plus d and a minus d. But over here, it's lopsided. And so what that means is that one distance, not all distances will fit. And what that means is, so for instance, right here, if we have absolute value of b minus c, that means that all of this distance is what we're considering. Now, if we take all of this distance and we move it and we see on one side of A, it actually won't fit because this distance will actually leave the allowed confines of our bound. So that wouldn't work. Then what we can try to do is we can try to grab C minus A. And C minus A is just all of this distance. And again, it doesn't work because if we try it on the other side of A, we see that it leaves the boundaries of the epsilon, and so it wouldn't hit. And let me just draw the boundary so it's a bit more clear. So right over here, there's the boundary. Right over here, there's the boundary for an x, which would stay inside of it. And so as we see, it leaves. Now, if we take A, this can seem confusing, but A, that distance is all of this. And that, I think everybody can clearly see, that leaves our premises. So that didn't work. And A minus B plus B minus C would be all of this distance. And again, that wouldn't fit. So the distances that would fit would actually be b minus a, because if you take b minus a as a distance right over here, it works on our left side. And then if we try to move it to the, we try to move it to the right side, trying to move it, there you go, it would still work. It would still stay inside the confines. So in this case, it's actually none of the above. Okay, which of the following functions have exactly one horizontal asymptote? So when we're thinking of horizontal asymptotes, what we're thinking of is as x approaches infinity, what happens? And as x approaches negative infinity, what happens? Okay? So let's take a look over here. So, and what we want for there to be an asymptote, it has to reach a limit of L. If it reaches a limit of infinity, then there's no asymptote there. So over here, if we factor this, so we get as x is approaching infinity, just to keep in mind limit, and then we can factor out 2 to the 2ex. So 2e to the power of x. To e to the power of x. Then inside what we're going to get left is 4 plus 6 over e to the power of x. And this would cancel out. And then as x is going to infinity, 6 over infinity is going to equal to 0. So what we would get is 1/4. And so there's our asymptote. Now, if we took negative infinity, actually, if we took negative infinity, and that's where you need to check. So now let's say we have x is equal to negative infinity, right? What would happen? So then the 2ex would cancel out and we'd be left with 1 over 4 plus 6 to the ex. So now when x is going to negative infinity, e to the x is actually equal to 0. Because think about it. If we take e to the negative infinity, that would be 1 over e to the infinity, and 1 over infinity is 0. Sorry, and 1 over infinity is 0. I think that's what I said. I don't know. I might have said something else, but 1 over infinity is 0. So then what do we get here? It's going to be 1 over infinity, because 4 plus 6 over e is 0. Wait, e to the negative infinity is 0, so 6 over 0 is infinity. So we would get 1 over infinity, which would equal to 0. And what that means is that we actually have two horizontal asymptotes. One while x is approaching infinity, and one while x is approaching negative infinity. If you don't believe me, let's check. We have our good friend Desmos, if I can make it pop out. There you go. There. Everything is not going according to... Okay, there you go. Just did something. There you go. So if we do our Desmos, and I can clear all my drawings, it was 2e to the x over 8e to the x plus 6. And as we see, over here we have a limit of 0, and over here we have a limit of our 1/4. Cool. So one horizontal asymptote, but we got two. That doesn't work. So okay, sine x over x. So sine x over x, what happens there? So again, limit as x approaches infinity, and so as x approaches infinity, what's going to happen? So sine x always is going to be between 1 and -1. So at infinity, we don't know it, but what we do know is that down here, it's going to be infinity. And so something over infinity is equal to 0. And the same thing is going to happen at negative infinity, because something over negative infinity is still going to be equal to 0. So this one actually has exactly one asymptote. And again, if you don't believe me, which is totally reasonable, x, and there you go. We see it's becoming smaller and smaller. If we scroll out, we can see that it's actually just going to 0. Perfect. To 0. Arctan of x. Let's take a look. So, arctan of x looks like... You know, I'm not going to say what it looks like because that would ruin the whole point. What if you don't know? Well, you kind of need to know what it looks like. But in essence, if you think of the tan function looks like this. That was a horrible depiction, but something like this. And what this is representing basically is that at infinity, a tan of infinity is equal to pi over 2, and a tan of negative n. Sorry, what am I saying? You can't take as you approach pi over 2, there's an asymptote going to infinity, and as you approach negative pi over 2, you would also get an asymptote going to negative infinity. All this is to say is that basically arctan of x has two asymptotes, two horizontal asymptotes, because now I'm going to draw it. Arctan looks something like this, and at infinity, arctan is equal to pi over 2, and at negative infinity, arctan is equal to negative pi over 2. And so this one has two asymptotes. Now ln of x, it does not have any asymptotes. So ln of x looks like this. And so there's a vertical asymptote at x equals to 0. And then at infinity, it just keeps growing forever. And that's why there's no horizontal asymptotes there. Okay, this question I know gave trouble to a lot of people. So let's take a look. So again, I say let's take a look, like I can just skip them. So for any m, there's a delta such that when x is greater than a plus delta. So what does this mean? This means that we're approaching from the right side, because usually if we have something like here, right, we have an a and a plus delta. So we're approaching from the right side, and a minus delta, we're approaching from the left side. So all this means is that we're going to be approaching a from the right side, and f of x is greater than m. So what does this mean? That means that for any arbitrary number m that I can think of, f of x will always be greater. And that means that f of x is going to infinity and beyond. So if we take a look then, we're going to, as x approaches a from the right side, f of x is going to infinity. And that's right over here. As x approaches a from the left side, it approaches infinity. What did I just say? I said I. Okay, and over here, x is smaller than any arbitrary n. So if x is smaller than any n, an arbitrary n, that is going to be negative infinity right over here. Negative infinity. Because any arbitrary n, I can think of something smaller. And again, we have f of x is bigger than m. That means it's going to infinity. So that means that as x approaches negative infinity, f of x approaches infinity. If you're wondering what that looks like, so as x approaches negative infinity, f of x approaches infinity, it's going to look something like this. As negative x approaches. As x approaches negative infinity, f of x is going to infinity. And that is going to be, as x approaches negative infinity, f of x approaches infinity, that is g. Okay, so here so for x is smaller than any n. So again, this is just negative infinity for the reasons we discussed before. Negative infinity. And this is, so here, that's our definition of a certain limit. So as we get closer and closer to the limit, we can always pick an arbitrary number where we'll get an epsilon. And if you continue on past that arbitrary point, you'll always be smaller than that epsilon. And so that just means that this is approaching to a specific limit. And so that means as x approaches negative infinity, we approach a specific limit. So that is going to be d. And if we are wondering what that looks like, that would just look like this. So as x approaches negative infinity, x, for instance, f of x approaches 0. So we would get like closer and closer to 0. Finally, over here, as we discussed in the beginning, this is approaching from the right side, from the left side, and f of x is going to infinity, as we discussed before. So this would be so as x is approaching delta from the left side, it goes to positive infinity. So that's k. And that's it for today, for this week's Mobius. Hope I made some things clear. If not, you can always text and ask me or other people. Have a great day, guys. I need to start recording. That's kind of, there was